Hi, and welcome to another episode of Ordinary Differential Equations. We are going to start a new chapter today. That is the chapter on second order equation. So let's go ahead and see what is in this story for us. We started the course talking about second order differential equations to justify the course itself. Let's go back and see what was the story at that time. Second order equation, mathematically speaking, is any equation that has time, a function of time y, the derivative of this function y prime, and its second derivative, all the derivatives calculated at the same time. This is called second order differential equations. At that time, we justified studying this thing by saying that, in fact, every motion is an example of a second order differential equation. And the reason for that is Newton's law, F is equal to ma. Well, m is treated simply as constant mass. A is the acceleration, which is this y double prime. Force, well, there are all sorts of sources of force in nature. We are just going to concentrate on two of them. One is position dependent. An example of it is like a spring force, sometimes referred to as a Hooke's law. In that case, the force of a spring is proportional to stretch, and the stretch is indicated by your position. Second source of force is velocity dependent type forces. This comes under titles such as friction, drag, resistance, damping, and so on. In these cases, we are going to take the position that the drag force is proportional to velocity. Velocity is this y prime here. These two, of course, are both simplifications so that we don't get into a tough mathematical problem. Full story for these things will require higher level description. For now, this is more than enough for us. All of these problems are treated as initial value problem at this stage. IVP refers to a situation where at a certain initial time we have the initial position that's shown by y0, and y prime of t0 is going to represent the initial velocity. Mathematically speaking, we are just going to refer to these things as initial conditions. We are going to strip the meaning away from it, and it's just some numbers for us. So the value of the function at a certain point and the value of derivative of the function at the same point are going to be the data that are going to be treated to given to us as indication of initial value problem. Okay, let's go back and look at a little video to make sure that we understand what the terminology here refers to, and hopefully that's going to motivate what we are going to do. For a while, we are going to solve this problem mathematically, just so that we see the algebra that is involved. And then, just like in the beginning of the semester, we have modeling with first order equation, we are going to have another version of that, but this time it's going to be modeling with second order equation. And that modeling, we are going to rely heavily on the story of oscillation, which we talked about again in the very first lecture. And we are going to try to explain a variety of topics in this course based on that mechanical oscillation. So let's go ahead, and here is a video from Ya Physics Animations. Very interesting and clear as to what the topic is. So we have a spring here. A mass is attached to it. This mass is going to oscillate on this bed. There's going to be a friction between these two, and there could be a drag between that object and the air or the liquid that surrounds it. The weight of the object is shown here with this arrow. The reaction of the table on the object is shown by that arrow. These are not going to affect the movements. We are going to have several arrows here, restoring force, that's the force by Hooke's law, the force that the spring is exerting on the object, that is this pink or purple arrow here. And we are going to be showing the energy that this object is going to have and the energy that is stored in the spring when you are compressing it or stretching it. So on this bar here you see elastic energy. Elastic energy refers to the energy that is stored in the spring. Kinetic energy refers to the energy that is stored in the object because of its velocity. So as we start the animation, what would you expect to happen? What is going to be the status of these arrows and this bar and such? Try to predict what's going to happen, and then I'm going to start the animation. So what's going to happen to this bar? This bar is showing the entire total energy, and what's going to happen to this force here. Let's see. So you place your bets or do your thinking, and then so this is one of the episodes that you're going to be actively engaged in what is happening, and then we are going to start this. So let's see what happens. So the object started moving at the moment. It's imagined that some sort of rolling paper here is pulled up just like a seismograph, and we are making recording on that paper as the object oscillates. So the curve that you see here is really position versus time, but it is made in a vertical direction. So you notice what happened to our arrows. Let's restart this thing, and then so I'm compressing or stretching, so the restoring force is going to respond to that. The friction, we said we are taking it, to make the problem simple, proportional to our velocity, and you notice these two are steady. The energy dissipates because we have friction, so heat is generated in the environment and disappears, and the two components simultaneously go down. So that is the problem that we have in mind. We want to solve this problem mathematically. That's just an example of understanding what the second order equation could come from. We can understand a variety of aspects of this problem from this animation. Similar thing happens in the electrical side of the world. So if you are looking at the story of a circuit, and how do the charges in that circuit bounce back and forth when they are encountering resistance, inductance, and capacitance, you'll have a description that is very similar to this, but we are not going to describe that problem. We are just going to stick to the mechanical oscillation in our class. So let's go ahead and construct our equation. And then in the next lecture, we are going to have how to solve these type of problems in much more detail. So right now, we are just introducing the topic. So we said Newton's law says that F is equal to ma. Force of spring, let's write that by Fs. That's the force that the spring exerts on the object, and we are taking it to be just proportional to the displacement. The displacement is shown by y. In the constant of proportionality, we are going to show it by k. So force is proportional to displacement, that is y. Depending on how hard the spring is, we are going to have some constant k. So k is going to be referred to as a spring hardness constant. Those of you who are coming from engineering, you are going to study that much more extensively under the title of Ernest law. But right now we just have force is proportional to y, and when you stretch the spring, the restoring force, the force that is acting on the object, is in the direction opposite to your displacement. So if y is positive, then the force is going to be negative. If y is negative, then your force is going to be positive. Then we have force of drag. Let's going to show that by k. This force is proportional to velocity. Velocity is y prime. So we appreciate this thing by drag force on our hand. When we stick our hand outside the window of a car, faster the car goes, the higher the drag force is going to be. Again, we had said earlier, it's a very complicated force. Just to keep things simple, we are going to say that the force is proportional to the velocity v or y prime. This also depends on some constant that shows shape of our hand, the kind of density of the air that's on our hand, and lots of other factors. We simplify all of that by putting it under one umbrella of some constant c. And again, the drag force is going to be opposing your movement. So if velocity is positive, drag force is going to be negative. If velocity is negative, then the drag force is going to be positive. So this constant c, sometimes your textbook might show it by gamma or something, but I don't see a reason to bring in one more complication of a Greek letter here. Just write c, and that is our damping coefficient. So this is also a constant. So the total force, so if you want to call it total force, in this problem we're just going to have these two. Of course, you can have lots of other forces involved in your problem. So this is our force statement. So total force by Newton's law is ma, and let me, just for the sake of similarity, let's write this thing as force is proportional to y double prime. Well, that's what our acceleration is. So let me also reflect the same way here. So my double prime is equal to minus ky, and this is minus cy prime. Well, this equation is going to look a lot nicer if I write everything on the left-hand side and in order. So I'll have my double prime plus cy prime plus ky is equal to 0. So that is our second order equation. So that little animation we just looked at is an example of this equation. Well, you saw in that animation you stretch the spring to a certain location and then you let it go at a certain velocity, and your start of experiment can be any time. Let's label it as t0. So that's going to be the starting position. We call that y sub 0. And at the beginning you can give a kick to that block by hitting it with a hammer or something. So you can specify the original velocity. It's kind of hard to arrange physically, but you can think about starting the experiment at a certain velocity, and here we show it as y prime 0. Typically this t0 is just time 0 to keep things simple again. So our equation and that we are going to be dealing with this in this chapter is this. We are going to learn how to solve this. We are going to look at a variety of cases as to how these constants relate to each other. So far, these are just 3 positive numbers, but depending on how hard the spring is and how much damping you have, all sorts of different kind of motions could happen. Later on, we are going to look at a situation where there might be some other forces. So other than the spring and damping, we could have a third force. We call that typically an external force, like somebody there pushing the object in addition to these forces. So we can have an external force here that's going to be referred to as a derived external force situation. And then there are more advanced topics in this section, which refers to the issue of resonance, in another topic that is issue of beat that we are going to investigate. Those things are going to come up when we talk about applications and modeling. So let's go ahead, look at some very simple cases just to make sure that we have already encountered problems of this type in calculus to some extent, at least by recalling those situations, we will be able to appreciate what's going to come up later. So let's go ahead. Let me look at a situation where we drop one of these things, most notably this friction, and look at the rest. So I'm going to take a case that C is equal to 0 to make the problem simpler. Physically, we are going to refer to this as undamped, or if you wish, frictionless situation. And let's take a case where M is 1 and also K is 1. So our numbers are very friendly. So what is left from this equation? Well, all that is left is that the y double prime plus y is equal to 0, or y double prime is equal to minus y. Well, definitely from calculus 1 you remember functions where the second derivative becomes a negative of the function itself. What was the function that behaved like that? So just rummage through your memory and tell me of all the functions you remember. Which one was it that you take two derivatives out of it and then you end up with a function that is negative of whatever you had started with? I'm sure everybody thought about this already. So some of you like cosine. So okay, cosine of t has this kind of behavior. You take a derivative of it, it becomes negative sine of t. You take another derivative of it, it becomes negative cosine of t. And look, this is negative of what we had. So y double prime indeed became minus y. Another group prefers sine. So okay, well, what about sine? Well, yes, you take a derivative of it first, becomes cosine. The second time becomes minus sine. And that, in fact, is also negative of what we are starting with. So the fact that there are two independent functions that behave according to what's required here is going to be a constant feature of second order equation. There are two fundamental solutions, and you notice that if I multiply either of these things by number, by a constant number, same property is still there. If I have y is equal to, say, 3 cosine of t, well, the factor of 3 just stays true. So minus 3 sine of t, y double prime is minus 3 cosine of t, which is again just negative of what we had to begin with. Same story with sine. So if I multiply it by any constant, say 5, I differentiate 5 cosine of t, differentiate again, beginning, this is negative of what we had to begin with. So can you think about the way of putting these things under one umbrella, that we'll have a solution that refers to both sine and cosine? We are not discriminating discriminating against either of these possibilities, we bring both of them into the mix. What can you think I can do in this simple case to combine the solutions that I have? Now, those of you who have taken your physics class are familiar with the so-called superposition principle, where you see small waves that the system can have in response to different stimuli can be added to each other if you act with those stimuli at the same time. Here, mathematically, it means if I add these two solutions, and the second derivative is also the sum of these two second derivatives. So it's minus 3 cosine t minus 5 sine t. Yeah, that is magically negative of whatever we had at the beginning. And of course, there isn't anything special about these numbers. Any constant number will have the same property. So y would have been a cosine of t plus b sine of t, where a and b are any constants you wish. So in first order equations, we always had one constant, some c showing up, which we played with. Now we have two constants. That's a standard feature of second order equation. If you have a second order equation, it's going to have two constants. That's going to refer to how to tie down things related to initial position and initial velocity, and so that's a main thing. Moreover, some theoretical statement. This is all there is. These are the collection of all the solutions of this equation is this expression. There is nothing left out or anything that can be created that is not already covered by this. We are going to perhaps talk about those theoretical statements later on, but right now this is the entire category of the solutions. So let me ask you to go through some other exercises. So suppose I have m is equal to 1 and k is equal to, let's take a friendly number, 4. So my differential equation is the following. Now what I am expecting you to create for me is this general solution. So this is referred to as a general solution. What is the general solution of this equation? Y is equal to what? Again, think about it a couple of minutes. Try the solution that you are suggesting. See if it actually passes your investigation. And then come back and tell me, well, the general solution is such and such. So, of course, we want, after two derivatives, I want a factor of 4 to be born out of differentiation. So how do I create a number? If I have a multiple of a t, when I differentiate, that multiple comes true, and when I differentiate again, second occurrence of that same number comes true, and then I can have the number that I want in front. So if I want to have a 4 here, I need to have a 2 here, which means I need to have 2t here. So here I need to have a cosine of 2t and b sine of 2t. Now I'm sure you can guess quickly what will happen if I pick another friendly number. So if I have y double prime plus 9y is equal to 0, y is equal to what now? Again, now you have only 1 second to tell me. So I don't even have time to show you the picture. It must already be flashing in your head as to what this thing is. What is it? A cosine of 3t plus b sine of 3t. Okay, let's up the ante. Tell me what will happen if the mass was 25, k was still 9. So my equation was reading like 25 y double prime plus 9 y equal to 0. Okay, I give you now maybe 5 seconds to tell me what the answer is in this case. Okay, 1, 2, 3, 4, 5. Time's over. So what do we do? Well, let's maybe simplify it for ourselves so the problem looks like what we have seen before. And 9 over, I divide by 25 just to say that this problem is already something that you have looked at. So what did you do to get 3 out of 9? Of course, everybody by now figured it out. This is the square root of that number. Well, same story applies here. So y is equal to a cosine of, that's going to be 3/5 of t, and b sine of 3/5 of t. Okay, let's go for punchline. What about the following problem? So instead of just playing around with numbers, same thing can be done with parameters. M and K is mass and spring constant. So of course y double prime plus k over m y. And the solution of this is y is equal to a cosine of what now? What should I write? Yes, square root of k over m t plus b sine of square root of k over m t. So in physics or engineering classes, you concentrate on this number quite a bit. You refer to it as the frequency. Frequency is just a multiple of t in this context, or mathematically, that's how we look at it. So here we have a frequency. Frequency usually shown by omega or omega 0 or something. Omega 0 is k over m. Okay, so in your physics or engineering classes, you do come across this. You probably did already. And here is the mathematical justification of why that formula relates to frequency. So what mathematics does for us is quantify something that we might notice in a lab or just everyday experience, and gives us some appreciation as to what's going on and how to control things. Like if you want to change the frequency, you have two modifiers. You can change your k or you can change your m and adjust the frequency accordingly. Okay, so this was a simple case that we could solve by simple consideration, recalling functions from calculus and so on. Let's go take a look at some other example again. To keep things simple, I'm going to be dropping one component at a time. Suppose my m again is 1. This time I take this spring to be very weak or non-existent, so I'm going to take my spring to have a spring hardness 0, but I'm going to have some friction, so I'm going to say C is 1. So what happens? My equation is y double prime plus y prime, that is, let's see, this is 1 y double prime. Let's just color coordinate these ones to see who is what. And this is the coefficient of y prime, and we always have a y, but now its coefficient has become 0. So now let's see, this is this one. Okay, so we are taking this extreme case. The spring is pretty weak, and so that we can actually solve it and say with the knowledge we already have, we can attack this problem and get an idea what's going to happen. So mathematically speaking, your equation boils down to y double prime plus y prime is equal to 0. Again, you might have seen this kind of equation in another context, maybe calculus even it by itself. But let's look at the methods that we have talked about so far and see what is it that we can use to solve this equation. Second order, so if we make it first order, our life will be easier because we have seen plenty of first order equation. So what's a simple trick that makes this thing to become first order? Again, think about it. What kind of things I can do to this to make it become first order? The name of the method starts with the letter S. We had the whole episode talking about that. What do we do? So again, you think about that and tell me, what would you do to make it first order? Well, yes, it's substitution. Meaning what? Take y prime, call it w. So y double prime becomes w prime. So your equation reads like what now? It reads like w prime plus w equal to 0. So what is that? It's first order. So what we did here is called reduction. We are going to have a whole lecture on that later on, but right now this is like a baby example of reduction. So what's the solution of this? Well, this is perhaps the simplest differential equation. You can solve it by guessing from your knowledge of calculus. You can do by integrating factor, you can do by separation. There is no shortage of methods. Let's be quick here so that we get out of this thing quickly. So w prime is equal to minus w. What's a function whose derivative is negative of itself? Okay, so I could have asked that question when you were in calculus 1, and you should have answered almost immediately. The function whose derivative is negative of itself is, of course, exponential of minus t. Such a function, when you differentiate, that minus comes in front. That is this w prime. When you want to differentiate, the derivative of exponent is minus. It becomes minus the formula for the function. So that is just minus w. So we already have the solution for this thing. But again, let me insist that you go ahead and solve it with all the methods we have seen. Integrating factor, separation, and so on. And make sure you get the same answer. Okay, I know what the w is. The original question was about the y. So now I'll come and say, well, w is w. Let's recall that the w was taken to be y prime. So y prime is equal to this. So y prime is equal to a exponential of minus t. And the question is, what is y? Well, it's just simply the integral of this thing. So a exponential of minus t dt. When you integrate that, what do you get? So again, you have about 2 seconds to integrate this thing for me. The integral minus a exponential of minus t, and then we need another constant. So let's call it that constant b. So the solution of this equation is some multiple of exponential of minus t and then some other constant. Well, what we are going to be dealing with in general is, what about the situations where everybody is there? So I have cy prime plus ky equal to 0. We want to have a method that works without taking all these simple cases. It has to work for all possibilities of MCK. We want it to be robust and quick, and that's what we are going to talk about in the next lecture. So the question is, what do you expect of y to be? What we are going to see that the solution is going to be consisting of either trig function like sine and cosine, or exponential function, as you see here, or the polynomials. In some cases, we are going to see a factor of t also present. So we are going to see the mix of this trio over and over in this course, because they are the simplest examples we can work with. They consist of three types. One is polynomials. Polynomials are like t squared, and so on. This is what you have started your algebra back in Algebra 1. And then we have these exponentials. These kind of functions are going to be in our mix. And then, of course, trigonometric, by which we mean just sine and cosine. The other trig functions are not as nice. So isn't it nice that the acronym spells PET, and these functions that we are going to work with are as nice as PETs. So we are going to have pretty much of the semester revolving around these three types of functions. Again, mostly because they directly relate to most basic experiment, that vibration experiment. Everything is explained in terms of these PET functions, and it's also nice that they are also easy to deal with. Okay, so our plan for next time is to start with this thing, learn the algebra of how to solve it, and learn all the basics of it, and if we have time, we come back and talk about some of the theory that is relating to this. Okay, so until next lecture, good luck and God bless.